physics, chemistry? I mean, it's mixed? Physics, all of you are physics. Okay, but still, yeah, like let's say carbon, right? Graphite and diamond are carbon is the easiest example, so saying about carbon, but if you find diamond somewhere, what does it mean? There is a high pressure environment. So when you can map the compound or the mineral that's formed there, it also tells you how this compound, I mean, what is the environment in which this mineral has been formed, the temperature and pressure. So depending on such phase diagrams, you can figure out how the thermal evolution of that environment has been, right? And the rock types, so again rocks are different, like on earth you find metamorphic, sedimentary, igneous rocks. Yeah, this you study in school, right? So, but on moon you don't find, let's see, what wouldn't you find, or what will be the most common rock? You remember, you studied this in 6th standard maybe, is it? Igneous, metamorphic, nobody remembers 6th standard? Huh? Yes, right, and even metamorphic, very not. So igneous, because it's more of volcanic rocks, right? Whereas if you go to Mars, sedimentary rocks are possible because there's been flow of liquid, etc. So you see, finding the type of rock is also important. Mineralogy doesn't tell you that, because basically rocks are aggregate of minerals. So there won't be a rock with a purely a particular mineral. Isotopic abundances are very important. Like yesterday when we were looking at the chronology of the solar system, you know, the timing comes from looking at isotopic measurements, because a particular ratio of certain isotopes tells you how long this rock's been there, right? So isotopic ratios are very important constraint of the timelines of these systems. So the techniques used are, we use remote sensing techniques. The near IR reflectance spectroscopy is a very common method used in remote sensing of planets. Basically a very generic instrument that you practically fly in almost every mission. X-ray fluorescence spectroscopy, gamma ray spectroscopy, will come to those in the next slides, just a bit on the principle of you know, how you measure them. Mass spectrometry techniques specifically for isotopic abundances. These are not, most of such isotopic measurements are not done in remote sensing, it's more with the samples. Like interior of the moon, yesterday we spoke about seismometers. So yeah, so that's probably the only way to really look at interiors, and for that what do you need? You need to have landing, right? You can't do this as a remote measurement, you need to have a contact with the surface. So such things can only be done from a surface. Planetary atmospheres, I've just put in a few, there's a lot of things you can do, but in very general, when you do atmospheric measurements, you want to know the characteristics of the atmosphere, like the dynamics. Like in Venus, for example, you have very thick atmosphere in Venus, there are clouds, so you want to know the cloud speed. Some may depend on the rotation of the planet, some component will, but like the Venus, actually the surface rotates very slow. It's almost 243 days or so, check the number, but it rotates really slowly, but the clouds rotate much faster. So you know, it's an open question what leads to the super rotation of the atmosphere of Venus. So temperature, pressure profiles, you know, how the density varies, right? And that's how you divide the atmospheres into layers, like on Earth, right? Thermosphere, mesosphere, you divide like that. Many kind of visible camera are used for this, like for cloud tracking, etc. You can use Doppler imaging. Sound speeds are measured, which is because the sound speed is dependent on the density and pressure. IR, microwave, many techniques like that. Planetary geology is a very important tool based on images, but you know, images do tell you a lot of things. High resolution imaging and topography. So topography means it's a 3D image. It's not just, you know, how it is, you also can see the ups and downs and really see how deep it is or how big it is. So making a digital elevation model, as you said, as we say, gives you an idea of how these structures are formed. Like yesterday we spoke about like Mars has Olympus Mons, which is very high because of the low gravity. So forming such features also give you an idea of the time scale and the and at those conditions, subgravity conditions of those planets. This is done in optical with radar, laser altimetry, in which you fire a laser from the orbit. Yeah, this can be done from orbit. So you fire a laser from an orbit and you get back the signal, and the delay tells you. So if you have two surfaces like here and here, the delay that the laser comes back will be different, right? So you can do that. So if you can do that at very close points, you can get a profile of how that is. Like if it's a crater, you can do laser altimetry at different points and get the profile of the whole crater. So that's done. But again, no one technique is enough, right? It just gives you one aspect of it. Just plotted images of this laser is not, I think laser is going to the next slide. There was the laser yesterday, right? Yeah, anyway. So from the left, it's a crater Copernicus on Moon. It's all the same, but you can see in different wavelengths and different methods. What do you see, right? On the left is the crustal thickness derived by Gray, which is a spacecraft that was around for some time. It's mainly to look at the gravity anomalies on the surface to really map the crustal thickness. Of course, there goes modeling and assumptions along with it, but basically there are models which from Gray later derive the crustal thickness on the Moon, and you can see the deeper blues are thinner crust. So you would expect that when there is a big impact, the crust would be thinner, right? Like those large basins, you expect crust to be thinner because it's being excavated. The titanium abundance, you can hardly see the crater. So that just means it's probably removed the top layer, and under that seems like there is not much titanium. Orthopyroxene is a particular mineral which is very common on the Moon, and you can see that the darker regions down, it's again lesser in orthopyroxene.
Sorry, this mic is not so good.
Oh, it's not.
Is it fine?
Oh, yes. Use the mouse. Okay, so I have to stand here and not walk around. Okay. Even the mouse here. All right, so that's titanium, that's orthopyroxene, and you can see the topography, as we said, like from a laser, for example, and the deeper blues are low, and the others are high. So you can see that crater, how the profile is, and see it has rings at the end where it's higher, and there's a deeper area, and in the center, if you can see, there are some lobes which are at a higher. So it helps you to study the morphology very well, like how exactly it excavated. What's the use of this? Like how deep it has been. Also tells you about the impactor, like the angle in which the impact would have happened. Say it's an oblique impact. You don't expect so much of excavation to happen. Or if it's a lighter impact, right? So the morphology of the crater gives you an idea, and I mean, people actually do modeling of how the impactor would have happened. How does this help in turn? I mean, overall on the Moon, you can study the population of such craters and decide, did all of them have similar impactors? Did they all happen at the same period in the history of the solar system, right? Or were they isolated events? So it appears, if you look at the Moon, there was an increase in bombardment, which is called the late heavy bombardment. Still under debate, but yeah, that's an era where. So you imagine this is all after Moon has formed, isn't it? So this is after the big impact on Earth, which means even after that, there was a period when bombardment was happening in the inner solar system. Again, this has impact on when life exactly would have come on Earth, right? If you have had these big impacts, it's unlikely that, or it could be that there was a certain period it was there and then could have been completely eliminated by such, just like the dinosaurs, right? We don't know yet, but yeah, I mean, that's seems to be a really valid reason. So that's the actual visible image of the crater. So high resolution imagery is not just pretty pictures, actually tells you, for a, I can't tell, but a proper geologist will be able to really write a whole paper with an image like that. Right? So you can see those rings. So can you say what angle would it have impacted? Huh? Yeah, it's a normal incidence, right? Because it's pretty circular. Just saying simple things, but yeah, you can make out more things from it. And you can see that there is a crater wall. There probably been maybe some infall there, and the center area is very smooth, which means it's been filled by the impact melt. So soon after an impact, because of the heat, the material there would melt, right? And then it will solidify again, right? So the more such impacts, so the main one difference would be, if you see a lot of craters, that means it's an older terrain. Whereas if you see a smooth terrain, that means it's been filled by this impact melt and erased the older terrain. So it's a younger terrain. Is that right? You have to do a modeling. So now from that DEM here, you know this exactly. So for this size of the crater, at least for the moon, there's a relation that's been worked out by looking at the full population of craters, that to produce this kind of crater, you need this kind of impactor, the mass diameter relationships. So it's a lot of modeling based on that. So there is no, I mean, yeah. Okay, nothing in science is like direct, but yeah.
Even if the impact was oblique,
Uh.
then also like because it had very high energy, the impact would be explosive. So it would cause pressure waves on the surface to go around the side.
Yes.
So that would go in circle, right? So the crater
That
would
would.
still form a circle.
Right.
Even if the impact was oblique. So how can you say that impact?
Yeah, but I mean that may be true for a certain range of angles, but you do see craters like Mare Crisium, which I don't have here, which is elliptical. So
You can't directly say that from the circular crater the impact
it's basically the modeling aspects of it. Like it's explosive in the sense it's more like the impactor is also gone, right? So everything melts, but the shock wave is circular, as you said. But the initial impact and the point of impact is oblique, which modeling shows that you can make out the angle with respect to that. So the final formation, as you said, is basically because how the shock waves go. So if this is at the edge of two very different terrains, probably this may not true. But if you are in a, because the property of the surface also has to be taken into account. So if it's a terrain where the materials are all assumed to have the same strength, structural strength, viscosity, etc., probably this would be right. So this is a young crater. You can see inside there is not much cratering. The impact melt that's been produced at the time of the crater is still there, right? So if you see a lot of craters inside, that means it's going to be very old. And when it gets old, you would not also see the structure very well. It gets erased with time, even on the moon, because there is weathering. Now, what kind of weathering on the moon? It's mainly the solar wind, which interacts with the regolith, and even micrometeorites break it down. And that's why the surface of the moon is completely covered by what you call regolith, which is kind of unsorted soil. Contains all centimeter size and even micron size particles. So the entire moon is covered with that. So it's not a crust, right? We don't see the crust as such. What you actually do when you do remote sensing or even bring back samples is this regolith, which you call. It consists of all these pieces. So imagine a smooth crust which is being bombarded for billions of years and converted into this material called regolith. So regolith is a term you use in Earth as well. In the case when you say lunar regolith, it's a result of this bombardment by micrometeorites and solar wind, which is not there on Earth, right? We are protected by the atmosphere. So,
from these pictures, it appears like the crater is very shallow. But
yeah. It's deep. That's why, because of the DEM. I mean, it's a, yeah, right. Because visually you don't find it. That's why 2D images won't be enough. Right. So you really need to do the topography. So that's a very close-up view of the inside part of it. Like, can you see that inside those central peak, as you call? So you can see very beautifully these images and the shadows. So again, imaging on the moon or any other planets is one of the main things that you have to prepare for is this shadows. So now you can't see this part of it. So now you might have to do another image when the sun is at an appropriate angle to do the complete. So these images don't sometimes come at one go because of the shadows. And on moon, you can also see that the shadows get longer when the sun angle is low and this is high. So that's the problem when you go to the polar regions of the moon. Because the sun is always at grazing incidence, the shadows are very long. We'll talk about landing in the South Pole a little bit. Just want to tell you the challenges ahead. Also just wanted to, already I said that when we say, because we keep saying composition, I just wanted you to distinguish what's rocks, minerals and elements. Because just doing elemental mapping doesn't really tell you what is the mineralogy or the other way around. And just knowing minerals don't necessarily give you what rocks it's composed of. But all three things are important to have a complete understanding of them. So these are just rocks from Earth. Do you have any collections? Is any of you interested in collecting these things? I had some many beautiful gemstones that you get, etc. Right? So the colors also mean something, right? If you're doing field geology, for example, you would collect peculiar looking rocks for certain reasons. The colors come from certain trace elements in that, like copper or chromium kind of things. So it says like in Apollo, I think up to, I don't remember which one, but up to in the initial few missions, it was mainly from commanders, pilots who went. But then once they took a geologist, Harrison Schmidt, he collected glass beads, which were very important. So you actually need a geologist to see which is an important rock to pick. So this is also very important. Like tomorrow we are having a mission to say go and collect some rock. You can't just pick what's there and come back, right? You have spent thousands of crores to go there and pick something, and you can't pick the wrong thing and come. So you should evolve a strategy by which I should know what rock to pick. So there's a protocol that you should define, right? These are all things for you in the future. So it's not just about science, geology. When we actually do such missions, even these things are important. Your time is so important, right? Even if it's a human or even a robotic sample return, you only have a very small window to go and pick, right? And so you have to either use some intelligence to pick the right thing, and otherwise, whole thing is a waste of time. So these are some sample types. Most of what we told today know about the moon today are coming from these lunar samples. Because though we do remote sensing, when something is in hand and we do very precise measurements in the lab, there's nothing that can beat that kind of understanding. So this is human missions. So they can collect bigger pieces of rock. Like this is 10 centimeter from Apollo 12, that's an anorthositic rock. Basalts, and they even did on the right hand corner, you can see drills. So a little less than 3 meter was dug deep into the moon. I think the last mission, Apollo 17, it gradually increased. They were doing cores like this. And you can see very different cores come from different places. And so that gives you a vertical stratigraphy as well. That's Chang'e soil. So China has sent 6 missions to the moon, and that's from Chang'e. And you can see the color of the soil. I mean, moon is very not colorful, right? It's very just gray, black and white kind of things. But moon soil is very special. You can see this is what we call the regolith. So when you scoop a sample and come back, it would be like this, some pieces of rock, melted glass, etc. But there is a speciality with lunar soil is that you can find glass spheres like this I'm trying to point. The glass sphere there is very, very smooth glass sphere. So where would they have come from? These are more from volcanic, explosive volcanic events, which would have cooled very quick and resulted in such spherules. The green glasses, so they are actually green, but just that it's very low in quantity. That again give kind of how this volcanism has happened on the moon. Agglutinates are very special only to the moon because they are a result of solar wind interaction with the regolith, so and meteorites. So even if it is a micrometeorite at very local scales, like in micron scales, they do have impact the soil, melt it, and fuse them together. So these are like products created there just because of such micrometeorite impacts. You can see them very black. So it's like melting them and fusing them again. Okay, so they contain something called nanophase iron. So they are very unique to the moon. Regolith breccia basically means rocks of different pieces of rocks are also put together by this fusing. So you don't really get a pure piece of rock from the crust. So you have to dissect these and find out which piece belongs to the crust or which piece belongs. These are very high resolution images of one of those grains, and these days because we have very yeah. No, it is very dry, but yeah, if you pour water, it's kind of sandy. That's how it would be. It doesn't bind together. Yes, yes. When we future, yes. It will take water, yeah, if you pour in there. But as such, it is very anhydrous. Like, actually, there is electrostatic charge as well because it's so dry. So it sticks to you, right? And the Apollo astronaut suits were also, they had these sticky things. And the grains are all, the shape itself, some are needle-like, so they can puncture, etc. So that's our technological challenges. Even when you send instruments, no, this lunar dust can be invasive and harmful for. So we can do X-ray CT scans now, so and look through the grain. And these are technologies that come latest. So when these astronauts brought back samples, like from Apollo, you have 382 kilogram, but it's not that they just opened up everything and looked themselves. There is a vision for the future, so it's only a small portion of that was looked at that time. And 50 years later, in 2019, another box was opened. And why? Like, see, there's such a difference in the technology that we can use. And there are still things kept for the future. So that's some kind of strategy that we all will take, right? We just don't open and keep for next many generations. Not much. I mean, it's only when, so it's uranium thorium. Basically, it's only on certain parts of it. Yeah, that's one of the first things they did when they brought back using a counter to see how radioactive it is. And some of the things you learned from the first thing, I think the first 2 missions, there was even a quarantine when they came back in case there is any biological material. But at least from so far what we have brought, there is absolutely no biological material. So we don't think at all that moon will have any possibility of life in the past. Whereas Mars, it's different. So if you bring back samples from the Mars, that's going to be harder to keep it contaminant free, etc. So they say not the regolith itself, but the finer part of it, because these are even few microns. They can be lofted. So there are pictures from the Apollo module, command module, where they've taken during the sunrise. You can see the, so yeah, possible. Maybe too low heights. And now, when I want imagery, I want to map at high resolution, there is never an end to it, because higher and higher you go, you see the details are getting more and more. I mean, you'll always find heterogeneity if you go deeper and deeper. To give an example, that's a whole map of iron on the moon. It's at 150 kilometer per pixel. I mean, each box there. So that's the resolution it has. You can't tell within 150 kilometers. That's quite big, right? What is the difference? Now, if we take that part of it here, you see the round maracretium on the right side. That's a map of Marek-Risham iron from class on Chandrayaan 2, which is 15 kilometer. And you can see now how diverse it looks. That's not from the same, but a lunar meteorite. And you do an X-ray map. And you see how, within that, how diverse it is. It's a 2 millimeter is that line down. So it's a few millimeter wide. So composition at different scales tell you different things. But doesn't mean, I mean, you can't always go and take samples and come back and try to learn about the moon, right? Then it's going to take forever, because you can only take from a very local region. So global maps are important because you get that overall for broad, answering broad questions like did Earth and Moon form together, it's important that we do global mapping. That gives you that overall perspective about it. So all of these are important and needs to be done with different strategies and different instrumentation. Also just wanted to mention what is the source of information when we do planetary science. What are the ways? And see, in astronomy, when it's mainly using ground telescopes or space telescopes, and of course modeling, simulation, etc. But in terms of instrumentation and techniques, the source of information in planetary science is much wider. Like we have meteorites, right? So meteorites are free. You don't need to spend money to get a meteorite, in the sense to get a sample from, do a mission and get a sample, you need you need to spend much larger amounts, but meteorites are really free. So they are, but they are pieces of material from different asteroids, Moon, Mars, etc. So they're very valuable. In the meteorite database that's mentioned there are more than 77,000 meteorite names listed. So you have falls and finds. Some you might see in a newspaper that you saw a meteorite falling, and if you can go and pick it at that time, that's more valuable because it's not contaminated by any terrestrial environment and you can just pick it fast. Then finds are just if you find them. I think in India it's not very common to look for meteorites, but you might see that go to the west, a lot of people who will be selling meteorites, no? Because you find it in some isolated areas, and it's a good business, right? And out of that, there's a 704 lunar meteorites. When we say confirmed, actually we could only confirm there are lunar meteorites after the Apollo sample returns. Till then, you are not really sure about the source of it. So even now, we call some of these meteorites Martian, but based on our understanding of remote sensing data, but maybe the real confirmation comes when we have a sample return from Mars. And most of the meteorites are found from Antarctica. Why? Not about that really. Yes, actually, that's a simple reason, but yeah. So it's a cold desert, yeah. So and no, nothing happens. There is no movement or changes happening. So there are these Antarctic meteor hunts, expeditions done. If you have heard of that, you can apply for that. So if you are a scientist doing meteorites, you can apply for funding to go to Antarctica. Isn't that motivating to do meteorite science? Just going to Antarctica is good. So yeah, and even in deserts, like hot deserts like Thar and etc. Yes, you can, but most often it's done in Antarctica as groups. Return samples, which is very, very valuable. Apollo, as I said, is 382. Then lunar missions is the USSR missions, robotic missions, which went again in the same time scales at the end of 60s and 70s. You might think like Apollo is like several hundred kg, but this is only 320. But you have to understand that when Apollo missions were human missions, USSR did this robotically. When in the early 70s, right? So that's remarkable achievement. So even though it's 320, it's like a completely robotic mission. Chang'e 5 and Chang'e 6, of course, are robotic missions, and that's what they brought back. There are like at least 100 just nature and science papers from Chang'e 5, because every micron that you get from it is worth writing a paper. And Chang'e 6 came in June 2024. So a lot of results are coming out, and that's the first time went to the far side of the moon and picked a sample. I mean, all this sample cataloging is done in that website, like you get photographs. If you just want to yourself do some study about it.
In the previous slide, we have seen that the Fe composition of the face side of the moon. Can we tell that like only due to these craters still Fe came to the surface of the moon, and could we expect? Do we have a speculation of what can be the metallicity of the far side of the moon?
Yeah, far side in remote sensing you get to see the far side also, because how do you do remote sensing? You have moon here, the spacecraft is going in a polar orbit and moon is rotating under that. So you do see the full moon. I mean, it's only when from here that you can't see the far side. From a orbiter you can measure. Iron content here is higher because these are the big impact basins and has got material from deeper into the surface. Far side has much lesser. So again, don't know why this asymmetry between the near and the far side, but this kind of asymmetries are there everywhere, like Mars also. If you look at the topography, the northern lowlands, and this kind of dichotomy seems to be there in many places. In situ measurements, so after meteorites, then this is all about missions where either return samples, or then you can do next best thing if you can't do a return sample is to do in situ measurements. You have to land, take instruments and do the measurements over there from a lander or a rover, and in the Mars even have a helicopter, right? Remote sensing from an orbit, that's the comparatively easier thing to do. So you can be in a polar orbit so that you can do global mapping. And ground telescopes, they are still useful sometimes to like for example there are I've just mentioned what's done here. So like from GMRT, Venus temperatures, brightness temperatures have been looked at. I have a student who's doing from Kavalur looking at the lunar exosphere to see the sodium line. So it's still valuable to look at the moon from ground telescopes. Again, in terms of the resources that we need and the time that you can use with ground telescopes is much easier.
How is the outer period or layer of that shown in the previous slide form?
Oh, here. Okay, this is more of a, because it's a meteorite, it's a crust. So when you get meteorite after a long time, sometimes on Earth, thin crust forms. So you will chip it off. But geologists or those who do this will know that the first layer has to be cut off.
Have you found any metal oxides, such things?
Yeah, metal oxides are everywhere, like see iron, titanium, they all exist as oxides. So yes, so that's one reason for interest on the moon in terms of mining or like getting these metals. Okay, just a nice plot, a bit old, but basically saying most of it is from Antarctica. So just to get a little more insight into how this is done, this is a near IR spectrum. So near IR is up to, let's say, 3 micron or so. Beyond that you will call it thermal IR. This is in the region between 1 and 3 micron from the IARS instrument on Chandrayaan-2, and you can see here an absorption feature which is related to the presence of the OH bond. So that's a very important thing of the moon. You would know that one of the major discoveries that changed things was presence of global hydration on the moon from the moon mineralogy mapper on Chandrayaan-1. So I mean, until then, because we have mainly everything from the samples, it was thought of that there is very little water on the moon. Of course, it's very little, but now it looks like it's not just the south poles. You can form water. When we say water, it's just about water molecule, not really big amounts of water, but you can form it by a process using the solar wind. So this is again a very real signature that IARS measured. On Mars, you have clay minerals. And just want to see the differences. So when you say you have a near IR spectrum, it's very different for the moon, and that's in Mars. So like near IR reflectance spectra really tells you about the mineral that's present there. So I'll come to the modeling of this in a bit. but it's very different basically. A little bit more on the moon. So this is how you do it. Basically, you have the spacecraft, the sun, the illumination from the sun falls on the surface, it's getting reflected, and you see it in the spacecraft. And what you measure is the reflectance versus wavelength. So that's the near IR spectrum that you see. Water itself comes from these vibrational bands of OH. So you can get overtones. So there's mainly 3 places where you can look for it: 1.5 micron, around 3 micron, and the 6 micron. You would have studied vibrational spectroscopy, right? So you know OH bond and how the H2O molecule can vibrate. So that's the mapping that was done for hydration. So the blue is higher amount of OH, which means naturally the polar regions which receives less amount of sunlight seems to have higher hydration. Also see that it changes. That's in the morning, in the same place in the midday it's lower water because of temperature, it's evaporating, and in the evening it gets again settled down. So morning, evening in moon is low, is not our, right? It's one day is 14 days. So it's in that scale. And so changing hydration. It's a very important discovery. It's not just the small band. This is a lab spectra, but it's taken from 0.25 micron all the way to 250. You can see for the same, it's an orthosite mineral. You can see how the features change entire band. Some of these absorption bands are present only in the near IR, but like if you go to 7.5, there is a feature there. So it's by identifying these features that you tag it to the mineral that is present. So like this, for example, this is from Kaguya. Kaguya is the Japanese mission that was in 2009. They have mapped the abundance of olivine in the moon, because we have to project in, this is in a cylindrical projection. So when you do such projections, you don't do the above 75 degrees. So that's why the cutoff there. And you can see these large basins on the near side has a lot of olivine, where you go to the far side, it's very less. That's Pluto, again just to show you a completely different spectrum. So Pluto from New Horizons, so this is a spacecraft that has gone, and now it's beyond Pluto. So you can see very very distinct signatures of CH4, CO, and ISIS kind of. So it's an icy region. So when you go to new places, one of the thing is modeling of this or identifying this becomes very challenging because like unlike in X-ray, which I'll come to the next slide, the position of this central wavelength would change according to the crystal structure. So these are arising from, say, vibrational bands, or in some cases like the moon, electronic transitions in crystal field transitions, like say iron 2+, there is a particular band at 1 micron and 2 micron coming from the split energy levels of the electronic transitions. So that the central wavelength would vary according to which crystal you are in, because the field changes. Therefore, it's sometimes very difficult to model this using only physics. And ideally what you want to do is from this find out how much of that is there. For that, what would you need to do? You should know this much depth of the band means the abundance is something. I mean, very superficially you can say the deeper the band, the more the material should be, right? But it's not that straightforward because of various factors, like there is scattering. You have to basically do a radiative transfer model to really figure out.
From surface composition, how certainly we can say the core composition of the planet?
No, core composition we cannot say at all. It's only modeling, because from seismology you can look at boundaries, and see, again, most of this is forward modeling, right? That's what you do in data analysis mostly. In the sense you first give a guess that if it is so, you will see this kind of attenuation in a seismic signal, and iteratively solve for it. And as you get information from various techniques like this, you put into the model and keep improving your model. So that's why, I mean, lunar core is still a question. We think it is there, and if at all, how big it is, not sure.
So instead of getting surface composition, seismic activity could tell more about it.
But seismic activity, as I said, does tell you where the boundary layers and where does the mantle start, or is there a boundary between the mantle and the core, and you have to put in assumptions of the interior. And core is very difficult in surface when you won't expect something to come, but mantle materials, there is a search for mantle materials among this, because we believe such impacts should have really penetrated the crust and brought in, at least from the upper mantle, some substances into it. So it's really unsure what is the mantle of the moon. We think it's more of olivine, but again, so the Chang'e 6 mission, one of the objective was to look for mantle materials. See, all this has to do with the giant impact theory, right? So then we'll know how exactly that happened, Earth-Moon system happened. Remote X-ray fluorescence spectroscopy, which can be done only in airless bodies, because like if you have an atmosphere, it's getting attenuated, so you can't do this on Mars or Earth or Venus, but on Moon, Mercury and asteroids. Like it basically works by this principle. That's a solar corona, and the corona is very hot and emits X-rays. So that's a spectrum from a solar flare that falls on the surface of the moon, and you get X-ray fluorescence, which gives you the elements that you want to see. So what is X-ray fluorescence? Basically, it's a photoelectric effect. Like, so if an inner shell electron gets ejected by an X-ray that falls on the atom, you have a vacancy, and a higher level electron can jump to this lower level, and if there is such a transition that happens, the difference in energy is emitted as a X-ray photon. Now, what's the uniqueness of this is that it's a very unambiguous signature of that atom, right? I mean, if you get a particular energy which is equal to the difference in energy levels of the atom, you can for sure say that it is coming from that atom. Right? You've studied, right? Like it's very unique, no? Atomic energy levels, there can't be overlaps, right? So that's very sure way of finding the elements. So these is actual spectra. So for example, this is from the instrument that we have on Chandrayaan 2 called CLASS, and you can see that here the difficulty in modeling this comes because because the X-rays from the sun are not the same all the time. As the sun gets active, it emits stronger flares. So did Arnab talk about flares? Yeah, so you have these flares from the sun, right? You know solar flares, right? Yeah, eruptive events on the sun. So a lot of energy is emitted in X-rays, and you can see that as you go to stronger and stronger flares, solar flares are classified as A, B, C, MX in log scale. It's just a classification based on GOES satellite, which is around, it's been there from the 70s. So depending on the intensity that you see there, you have this classification. You can see, you also get to see higher elements as you go to stronger flares. So the thing is, now you are looking at the moon and you're getting the X-ray spectra. But now I can find the element, but now if I want to translate that into an abundance map, I need to model this, for which I should also know what is falling on it, because that's changing. Whereas in the case of a near infrared reflectance spectroscopy, the sun is not changing its infrared emission, or in visible, it's not. But in X-rays, it's very dynamic. Therefore, it's challenging in the sense we also need to look at how the solar incidence is, even the angle and the X-ray spectrum is. So on Chandrayaan 2, we have another spectrometer that looks at the sun all the time simultaneously. So you can get this, what's falling from there, and you get it from here. That is again on Venus. I said it's not done, but this is on the lander. So there's been 2 landers, I think. Venera in the 70s, USSR, which went on the surface, and you can see the lines of magnesium, aluminum, silicon from the surface. It worked for 4 hours or so, then few hours, because the Venus surface is so hot, right? 400 degrees or so.
Have you landed on Venus?
We have landed on. When we meaning yeah. Yeah. But yeah, that's really remarkable, and this is like, even before I was born, when you might think, like, for me itself that's old. So that's very remarkable thing to have. I worked for a few hours, and after that we're not able to, I mean, it's really very challenging to have instrumentation which doesn't melt there, right? Even lead melts, so you have to keep up your instruments. Actually, instrumentation for space is really very challenging. You can do something in the lab, but to translate that into a flight instrument, first of all, see, the thermal environment is very different. If you take something on a spacecraft, the side that faces the sun will get very hot, and the other side is going to be cold space, so very cold. So you see, you have to have all of your instruments working in that kind of scenarios. So it's thermal designs are very important, and even Venus balloons were there at that time. The spectral quality is different, but it's remarkable that even that time they could do this. That's from this is the result finally. So you measure that spectrum, and you can see the map of magnesium aluminum, taken a ratio here, but that to show the contrast. You can see the near side basins having higher magnesium, and this was completely done by this UG students at IITB, so that's why it's nice. Yeah. And actually computer science students, they're not even physics, it's more of a data analysis exercise, right? So you can also do composition from visible or IR, but it involves a little more of empirical relationships. For example, you don't need even a complete absorption feature. Even here you can see a very broad feature. Even the slope of this can be converted to, because this band depth, the band center and the slope, all these changes depending on the composition in terms of how much of magnesium or iron, this is in the case of moon, is there. But a lot of lunar IR spectroscopy is based on the samples itself. For example, in this, for a quantitative estimation, what they do is they calibrate the reflectance with abundances using return samples. So because you have a subset of lunar compositions in the lab, you keep that as reference and do laboratory measurements at different angles or at the same scenarios that you are encountering in a remote sensing experiment, derive some relations empirically. And so you just find correlations. So it's not a physics based method in the sense you are not putting in the right equations, but you just depending on relations that you can derive between them. So what is the uncertainty here is that you may not have collected all example compositions of a planet. So you have only a subset, right? And from that you are deriving. So can have lacunae in that sense. But for this it is done, and people have done, see, that's like iron composition. Here it's titanium, and you can see specific areas where titanium is high. So why is titanium important? Because as you were saying about resources, titanium is associated most with ilmenite, which is a source, and wherever there is ilmenite, there is also an association with helium-3. So there is a lot of talk about how we can use helium-3 from the moon as a resource. Gamma ray spectroscopy, again that's also a very useful way to do elemental mapping. On the right side is shown a gamma ray spectrum of the moon. What I want you to note is that the black line is the actual observation, but the lines down is what is actually it is. So if you want to derive, what your aim is to derive this from this. What I mean is, here there are actually a lot of lines, but your instrument cannot resolve them. So you see this kind of broad peaks or very weak peaks here. What we are trying to do, so you see the difficulty, right? To get from this here, you need to really know a lot in the sense, first of all, you need to calibrate your instrument very well. Like I should know for each of this line what is the spectral resolution that's in my instrument. So you have to put in a lot of factors, like for example, they do what you call a spectral unmixing, like you put in these elements, what you expect, and then try and model what you observe. So that's a forward modeling. In the case of gamma rays, it basically comes from galactic cosmic rays interacting with the surface of the regolith. So these are nuclear reactions. So you can, we have fairly good understanding of what nuclear reactions can happen with the composition of the galactic cosmic rays and the flux. So you put into algorithms, calculate the physics of it. This is a physics based model, of course. So you calculate what is the expected flux, and then try and model that. So that's what is done in gamma ray spectroscopy, which has been a very useful technique because it can even do on Mars, because these are higher energies, while X-rays are soft X-rays, so even the thin atmosphere of Mars stops it, but gamma rays you still can do. So it's very useful technique. Again, gamma ray instrumentation wise, there is limitation on the spatial resolution. Like the class that I said, which is an X-ray spectrometer, can do a few kilometers, whereas when you go to gamma rays, it goes to hundreds of kilometers. So it's more coarse. That's why most missions would take a suite of instruments, right? You can't just say probably anything with just one instrument. So that's done with gamma rays. And there are also, you asked about radioactivity. So gamma rays can also look at radioactive elements which you can't do in X-rays, like potassium, thorium, uranium. So here you see thorium on the near side of the moon and on the far side. So it's a lot more here. So there's a region that's classified as Procellarum creep terrain. There seems to be a lot more of radioactive elements. Now, why are radioactive elements important? After the initial impact event when the moon formed and it's cooling, it depends on how much of radioactive elements it has, how much energy it's still inner energy it has still to melt what is inside. Like that is the only source of heat after the initial impact event. So if you have enough radioactive elements accreted to be able to melt, then you can see corresponding changes. Whereas if it's very low, there is no energy that's from there is no internal energy to cause further melting. Again, why is that important? Like, see, we do not know why whether moon had a lunar dynamo in the back then, but there is strong evidences now that probably it had. For a dynamo, it needs a liquid mantle. There should be some convection in the mantle. So see, all these are very tight. So you can see like one measurement and placing it in a broader context is very important. That gives you the whole picture of where we are going.
But you said there is a seismic activity.
In terms of, yes. No, that can be even contraction. Yeah. But magnetic field, it doesn't have a global magnetic field, but there are crustal fields. We believe it's due to impact related, but some of the samples have paleomagnetic fields, which shows that they formed in the presence of a magnetic field. So again, there's a lot more to discover on the moon. So just to summarize, the systematic approach is to do all of these X-ray spectrometers. So there's also this difference that because these are these photons have a certain energy, how much can they penetrate? It depends on its energy, right? So gamma rays can go deeper, whereas X-rays and NIR is looking at the very surface. So when you look at it in different wavelengths, it also tells you from what depths they are coming. So you can do X-rays spectrometry for the upper few microns, gamma ray for a little deeper, and indirect ways are reflectance spectroscopy or looking at visible reflectance spectroscopy. Again, these are also very uppermost layer. So you might think like, now I am actually looking at only the first 10 microns of a planet, and how much can you say about it? Just that on the moon, as you said, because you don't have any plates or you don't have any much of seismic geological activity, so it's like everything is standing still in time. There's only these impacts that are happening. So if you crush something at that spot, it's still there. So what you believe is if you had a nice smooth crust in the beginning, you're still seeing signature of that crust when you measure the regolith. So that's the basic assumption. Otherwise, no point in doing the first 50 micron soil. Here things are changing. So if you just do first for 50 micron and you dig deeper, you might find a completely different thing. But moon, you're not expecting that because it's just a layer over the other. There's another method with neutrons. So you just count the neutrons from the surface of the moon. Again, this is produced by GCRs, and there's a very nice method in which, just looking at the count rate, you look at it in 3 bands: thermal, epithermal, and fast neutrons. It's just defined by the energies that they have. If you see a suppression, that indicates hydrogen. So just like in nuclear reactors, you use water as an absorber, right, to slow down neutrons. Same thing here. If there is water, those energy neutrons will be absorbed more. So if you compare the counts in 3 different bands, you'll see that the middle band, which is the epithermal, will be suppressed relative to the other 2, which indicates the presence of water. And since neutrons come from deeper, like a meter down, this tells you subsurface water. So the blue here shows a suppression of neutron count rate, and correspondingly modeled is the water equivalent hydrogen. So WeH is water equivalent hydrogen in percentage. This is the south pole of the moon. You can see that there are certain areas where you expect more water ice. Why that's important? Because all our future depends on water, right? So if there is water in the south pole, we'll go there. Just quickly on just a bit of Mars. We started at 11, right? We started today properly, right? Okay, I'll go quickly. So these are just pretty pictures, but because it's from our Mars mission, I just wanted to show it. And these are global views. I know, see, this is from very far, but you can still see the polar ice caps changing. You could see dust storms, getting global views, right? So that's nice, but higher the resolution, you see higher features. This is high rise on Mars Express. Yeah. So you can see those features on Mars, and this is from Perseverance, beautiful views, which is still there, and this is very close up. It's Mahli, it's a hand lens imager, so it's actually a lens that they've taken there to look at it very closely, and you can see features which indicate flow of water, and there's been some sedimentation, etc. So such images are very useful. In situ experiments, that's Chaste experiments on Chandrayaan-3. So I'm just only giving examples, because no point in just listing all the in situ experiments that's gone. So this is the probe, just to give you a feel for what kind of instrumentation goes there. Can you see this is the probe that's here under the lander. So that was penetrated the surface, and from that model is the temperature. And you can see with local time how the temperature changed. 10 centimeter. So these are kind of measurements you can only do from a lander. So just to highlight that, right? You can't do remote sensing for this. You need contact. APXS, again that's an alpha particle X-ray spectrometer, and this is the path of the Pragyan rover. It stopped at all these places. There's a crater here. So that's Vikram lander, and each of these measurements, that's the whole picture. So that's from the top view, and that's where Chandrayaan-3 landed, and the rover moved. It's about 50 meter. It's small, but small step but big leap for us. This is taken all these measurements, and basically found that this is a fairly uniform composition, and also found some evidence for the hypothesis that we have that there was a lunar magma ocean. That's a seismometer on Chandrayaan-3. Again, it was lowered using a kind of pulley and placed on the surface. And those are the signals. So seismometers like this, it's a MEMS based. So it's very, very small device, semiconductor based device. And how does it work? It's basically spring equation. If you give an external acceleration, there's a small mass that moves. So depending on the displacement, you can figure out how much is the acceleration that's produced. And you can see the rover movement here. It's when there's a rover movement, you can see those spikes. And it was very sensitive. It recorded everything, like if the solar panel moved, some instrument opened its door, everything is recorded here. And so there's many 50 events, I think. 50 uncorrelated events were seen, yet to figure out are they real seismic or not. So if you are interested, you can go and look at the data and try and see, maybe looking at the pattern. And there's only been another seismometer on the moon from Apollo. So somebody can look at that. Also, these are images from the rover navigation camera. This is how you move, right? You first take a picture, think a lot about it, should I move there? And then all are again time constrained. This was there for 10.5 days. So because this is our first thing, like you sit and think, it's not like autonomous, you just decide. In future, when all of you are doing this, probably you will write codes to say, okay, if you see this, move to the right, left, yeah, but okay, this is our first thing. You can see there's a crater there. You know, what happens is when you take an image from the surface, you don't see many of these craters because it's too small for the resolution. Actually, you land, you start seeing features, right? And the rover tracks there, etc. So I think when it reached this crater, had to turn. Interesting thing, it looks very flaky. He was asking whether it will push together, but see, just because of that stickiness of this, it's sort of clumping together like flaky stuff. Right? So that close-up images also. So these are not just about the pictures. In fact, if some of you have engineering skills, you can actually, those who are in civil maybe, you can look at what is the force that the wheels are exerting here, how deep has it gone. Based on that, figure out the density, right, the wheel, how it interacts with the soil, which are all very useful measurements, because it's not easy to find density of the soil when you can't do from remote sensing, you have to bring it back, and even then it's not easy to real density of the sample. So these are things just from pictures probably you can do. Sample return, I'll just stop with the sample return. So this is one of the latest papers from Chang'e 5 where you can see this is a side view. So Chang'e 6 is from the far side, all other samples are from that area. Chang'e 3 there, and you can see the Apollo and the Luna. So far it's all been from a narrow belt in the equator. So see, everything we are talking about the moon is because the samples are from there, right? Now Chang'e 6 has, I have actually recent papers have said very important things which is very different from what is there. So as you collect more samples, you're sure to find new discoveries. For on Earth, if aliens come and pick from 6 places rocks and go back and say the whole thing about Earth, won't be right, right? Even though it's not as bad as that, because moon is not as complex as Earth, but still only from that samples we know a lot, but it's like if you go to different areas, certainly you are bound to see new things. So Chang'e 6 landed. Also wanted to understand how complex these missions can be, because we have to have the highest standards maintained. Like I said, if now see initially I think there was a very old Russian paper mentioning water in one of the lunar samples, but it was so much debated that actually because it came here, is it just absorbing water? See, anything you keep here, it will absorb water, right? It just how much can you believe this? So when we bring samples and have to publish something, we have to really show that we have kept it contaminant free, have other two highest standards to make sure our things are accepted, particularly if you're discovering something. If you're just going by others said this and we find this, that's fine, right? But in when you want to publish something totally different, this becomes very important. So that's a Chang'e 6 capsule, so we'll have similar ways, and curation, cataloging, and preserving for the future. So you put it in, you open it in very contaminant-free environments in glove boxes. So this is all being planned in the group that I am in. So like showing this a bit more, and the kind of measurements. Just one example that you particularly do are things like this. For example, this is when you say samples, you're looking at only, you can ask only for micron size samples. These are thin sections. So as somebody who does sample analysis, you need skill. So it's not just about understanding the physics or the chemistry. To cut this in the right, so you can't afford to cut and say, okay, went wrong, let me take the other one, right? This is a very important piece of rock. So you have to cut it at the right way, because otherwise your results are also going to be wrong. Because you need that thin section, you need to prepare the sample in such a way and get it. And from one of this itself, there's so much of results that you're going to get. So we need to prepare in India when we plan Chandrayaan 4, there's a whole lot of things that we have to prepare for. it's even about the skills that you need to acquire. See, as a medical doctor, learning something in simulation is okay, but you have to actually go and do a surgery, you need a skill, right? It's the same way here, you can read all this, but when you actually want to cut a rock, you do have to try it. So we plan to, do rehearsals of this, the whole rehearsal, like you bring the sample, how you will keep it, how you will cut it, how will you do it, kind of. South Pole, as I said, is very important. So Chandrayaan 4 and most of the lunar missions that's planned, like the Artemis and the Chang'e 7, 8, all are planned to the south pole of the moon. Why? Because that is where we are almost sure there is water either beneath the surface. And so what is there? All the globally, what everybody wants to do is the destination south pole. That's where we'll build habitats. That's where human presence is going to be there in the long term. Might sound like fiction today, but I mean, pretty sure that's going to happen. See, at one time there was this race to go to the north pole of Earth, south pole of Earth, right? You've heard of those stories, how people were racing to go there first. It's sort of similar situation now, but now we have stations there, right? Even we have stations in Antarctica. Know the names? Yeah, somebody said that, no? Maitri and Bharati, and yeah, right. So similarly, I think that's going to be the kind of framework when all countries are going to the South Pole. We'll have stations, particularly for that country, and do experiments from there. The difficulty is this: to find a place to land is pretty difficult. Why is not playing? This is every 2 hours frame of the South Pole in 2025. So you can see that every 2 hours how the illumination is changing. So now if I decide that I'll land here, I have to really keep that window, because it's going to be again night very soon there. Because on the South Pole, it's not like in the equatorial latitudes. Landing on the South Pole is much more difficult. And even the terrain is not really friendly at all. It's very rugged. There are a lot of craters there. So you get very small areas for landing. One of the main challenges in landing is what you will define as an error ellipse. Like I decide I'll land at this coordinates, but that mission will have an error ellipse. Like within this I'll land. For Chandrayaan 3, for example, it's a few kilometers. Like it's okay to land between that. Now you need like 50 meters error ellipse. So it gets harder and harder there. So and also the timeline. Like if you decide I'll go on January 31st to that particular area, you need to keep up that, right? Because otherwise it's going to be night again. And night here are extremely cold. It's like minus 200. Minus 250 kind of, and to survive there is extremely challenging even for the instruments. Forget operating, just to keep it alive is going to be hard. So I think that's pretty much I have. Just wanted to stop with what the future for you is and what the scope for you is if you get into planetary science. In fact, it's not just planetary science. Actually, it's doing planetary missions is kind of very interdisciplinary and a lot of technology involvement here. So that's our future, what we want, right? A presence there. And what do you have to do for it? None of this is really planetary science. It's more to do with engineering, in situ manufacturing. So talk about ISM, not interstellar matter, but ISM term used here is for in situ manufacturing, because you have to use the regolith there and make bricks. For construction, you can't expect to make that by taking everything from here, right? Because it's going to be very expensive missions. So there are groups even in India who's trying to use, for example, microwave. You can do microwave centering and make regoliths, bricks. Yeah. Building a? It's a hotel? I thought it's not a hotel. You want a hotel there first. Yeah, but then that is another constraint you are bringing in. You have to find a place with a lunar pit, etc. for landing. You don't get everything conveniently, right? The place where you want to land. So, okay, this is very fancy, but yeah. Okay, you can design it, but basically saying that you need to use the resources there. And assessment of risk, as I said, there are kind of quakes, lunar quakes happen, micrometeorites fall all the time. So you have to, whatever structure you make has to withstand all this. right? So there's a lot of things to do on Earth before you start doing this. So designing and like one of the conferences I went for, there was a complete session on lunar, architecture for this. Like architectural engineers are designing these things and even looking at the aesthetics and psychological aspects of this. Because suppose you go there and want to stay there for 10 days. No, it's about how nice would you find it there, right? Even you go to Antarctica, it's difficult. Now imagine going and staying at the moon, kind of. And ISRO, in situ resource utilization, is a very common, popular term that we use now. Basically, it is saying that instead of taking things from here, which is economically not feasible in the long run, we can have demo experiments, we can take small things and do. But ultimately, you have to do everything there. The life consumables like oxygen, water. That's why South Pole is chosen, because you believe water is there. Production of propellants, maybe you can make launch pads there. Raw material for construction, metals, everything should come from lunar soil. And as somebody said, farming also. We talk about lunar farming now. Chang'e 4, one of the missions took cotton seeds in a box and it sprouted there, but it was a very controlled environment. Like they have just the box and it did work there. So it's more about the gravity that's there, how it affects, right? But if you want to use that soil, there was a paper I think 2-3 years back where they used the Apollo return samples to grow a particular wheat and to look at its, how things change in its growth, etc. So, each aspect is very difficult and different field. And finally, why are you doing all this, right? You just not for a tourist spot. It's also things like astronomy from the moon. You heard about Pratyush. That's an orbiter, but ultimately maybe you can set up a radio telescope there. Fundamental physics experiments which you can't do here. The environment that moon provides may be good. And even the sky is great if future you have optical telescopes there. And it's also considered a gateway to Mars, going straight to Mars rather than. But of course now Elon Musk is saying we'll go straight to Mars. But so that's all. I just wanted to also put up some resources like where you where yourself you can see maybe remote sensing images. Basically because I think as physics students we don't study this. Even I did physics, so it's only later just learned all this. Whereas if you're doing geology, you use GIS based tools. So basically because this is more about mapping, etc., the tools that you use are different. So many of these have such tools available to look at data from these. And if you're doing spectroscopy, other tools are there. So QGIS is a very popular open source tool to look at maps. And yeah, all the and this is also a very nice site where from Open University, where it's the thin sections have been archived. So that's a nice project that somebody, a friend, professor at OU had mentioned, which I thought was interesting. Is like ultimately maybe you can do some AI based pattern recognition so that somebody can just look at those and say what it is, instead of now actually you put it under the microscope and do the analysis. Visually also, visual clues are also needed. And all the Indian space mission data is in this Pradhan. That's the name of this. Also wanted to mention there is a ASI symposium. I think the last date is coming up soon. So in case you are interested in astrobiology or organics in space, that may be something that you may be interested to go to. It's in Bangalore, but I think that's it. Thank you. You said you won't clap today.